In this lecture, we'll discuss the Dryad LINQ system, which is Microsoft's engine for distributed computation. So, a prerequisite for this lecture is the lecture on Condor, on the Condor distributed batch processing system, which is also there in the same lecture set. It's there in the same playlist. So, we'll first discuss the basic idea and the related work. Then we'll go through the design and the architecture of the Dryad LINQ system, and then look at two specific benchmarks, TerraSort, which is pretty much sort a terabyte of data, and the Sky Server benchmark, which is an astronomical benchmark for processing astronomical data. So the basic idea is that many of the current programming models for large-scale distributed programming, like MapReduce, MPI, Microsoft Dryad, are essentially of the same type. So they put a lot of load on the user. So they are kind of based on explicit parallelism, where pretty much a large part of the planning and the scheduling. So I'm not discussing planning and scheduling once again because this was discussed in the Condor lecture. So where we basically said planning is the mapping of resources, the mapping of jobs to pools of machines, and scheduling is running a job within a pool of machines, right? The time aspect of it. So MapReduce, just a quick overview. It essentially takes a large program, a large problem, divides it into a set of smaller problems, distributes the small problems to different machines, and again collects and collates the results. MPI is at an even lower level where machines just send messages to each other, and based on these messages, the final output of a program is computed. Microsoft Dryad is Microsoft's distributed execution system, where again a program is specified as a directed acyclic graph of jobs or tasks. So where you have task 1 and task 2, task 3 and so on, and these are mapped to different machines. But here again, there is the onus is on the programmer to actually divide a program into tasks, specify the dependencies between them when it comes to the dependencies are specified as a directed acyclic graph, and these run on the system, right? So these are kind of extensions of Condor. So a Dryad LINQ kind of extends this system. So it takes an existing LINQ expression, a language integrated query expression. So these are essentially expressions, programming language expressions in a .NET framework. For each expression is a side effect free transformation of the data. The side effect free is where essentially we can take a data and we can apply a set of functions to it, right? So then of course the data keeps on changing, but it is not accessing any external data. For example, it is not changing a file, not sending a message over a network, or not accessing any other piece of memory that is not contained in here. So this is a side effect free transformation, which is heavily used in functional programming. So LINQ expressions pretty much use that. And once a program is written using these LINQ expressions, the Dryad system parallelizes portions of the program and runs it on thousands of machines. So when you combine the existing Microsoft's distributed execution engine, Microsoft Dryad, with LINQ, which is a functional programming paradigm, so when both of them are combined, you get Dryad LINQ. And so this is kind of a state-of-the-art system. So using this, it is possible to write very simple code to sort a terabyte level data set in just 319 seconds, in just about 5 minutes, on a 240 node system, which is not much, right? So for 240 nodes, this is actually a very good result. So certain prerequisites over here. Before we proceed, users should have some idea of functional programming, particularly when a programming that does not use the notion of permanent state. So it does not use files and networks, and so it does not use even arrays. right? So it doesn't have pointers. So where you simply have data and you just apply a set of functions to it. So the notion of functional programming should be clear. Otherwise, viewers will not be able to appreciate this lecture. So functional programming here, we are talking of languages like OCaml, ML, Scheme, and so on. And of course, they should have some idea of a distributed batch processing system where we have a large number of tasks. The relationships, the dependencies between the tasks are specified as directed acyclic graphs. And the lecture on Condor, which is there in the same playlist, would kind of set viewers up for what is coming in this lecture. So LINQ, as I mentioned, is language integrated query, which is a set of kind of imperative and declarative constructs in almost all of the .NET languages, which is C Sharp, F Sharp, and VB, Visual Basic. So there are some, so this is not purely functional because a pure functional language will not have many of the imperative directives. So it is kind of like semi-functional and imperative. So the imperative directives are, of course, you have variables, loops, and iterators and conditionals, for loops, if statements. They are there, and we have standard. So we have a heavy. So we have a very strong notion of types, a very strong notion of inferencing types. So these are very strongly typed languages, and we have functors. So I will not describe the background of functors, but I would request the readers to look up the Wikipedia articles on functors. And in general, treating functions as high-level objects, right? So treating functions as separate objects of their classes, this notion should be clear to viewers before they actually proceed. So a quick scan of these concepts on Wikipedia would set up users for the rest of the 28 slides in this talk. So a brief review of related work. So of course, we always have SQL as the gold standard to compare with. So in SQL also, we don't specify how something needs to be done. Rather, we specify what needs to be done. So let's say we want to read a table and then we want to order them. We don't actually work at the level of sorting the data. So we don't say use quicksort or merge sort, for example. So this is a declarative language where you pretty much tell SQL what needs to be done. And of course, SQL has automatic parallelization mechanisms where databases automatically parallelize the SQL queries. Or also we have variants of SQL known as parallel variants of SQL. After SQL, we had a large explosion of these big data programming languages. And the most prominent among them was MapReduce, where of course we take a large problem, break it into small chunks. And so this is the map phase, which is that take a large problem, break it into small chunks, execute each small chunk, and then again collate the results. So this is a reduce. So of course, a lot of operations like sorting or database joins was hard, right? And so basically, so if you would see, two of the problems we have tried to describe over here from the paper are TerraSort and Sky Server, which essentially performs database joins. So both of them are hard to do in a MapReduce kind of setting. Also, the support for types in MapReduce is kind of weak. The reason being that that was never the mainstay of the design. So if there is any problem because of the wrong usage of types, for example, something is an integer on one machine and then it's read as a floating point on some other machine, there's actually no way to catch such errors. So then of course we have many domain specific implementations of MapReduce. So we have Sawzall, which is very popular. We have Pig, so that also was Yahoo's system, again very popular. And of course Facebook Hive, which is Facebook's rendition of MapReduce. So all of these are rather popular. So they use the same simplistic notion of a map and reduce kind of operation, and they are also a combination of declarative and iterative constructs, and they are inherently extensions of SQL. So in that sense, Dryad Link makes a marked departure and tries to do what Condor does to pretty much this area. So of course, this is, so as we had mentioned at the end of the Condor lecture, that Dryad Link is kind of a more modern avatar of Condor. So the first is that unlike MapReduce, which makes rather strong assumptions on the system, in this case the computation is not dependent on the nature of the underlying resources. So all the underlying resources are reasonably independent of the computation. The second is that we make a virtual execution plan. So here also the planning phase and the scheduling phase are separate. So we make a virtual execution plan which says that given a set of jobs, how will we execute? And then of course the plan is scheduled on a cluster of machines. And in the cluster of machines, a lot of things can happen, right? A lot of dynamic changes can happen. We can have faults, we can have outages, a machine can just swap jobs out. All of those things can happen. So that would be the scheduling aspect. But here also planning and scheduling are separate. So what the scheduler gets is a virtual execution plan. So the structure of a Dryad job, well, similar to Condor, it's a directed acyclic graph of jobs, T1, T2, T3, right? And then of course we can have a job T4 that is dependent on the completion of both T2 and T3. In this case, each of the vertices here is a program, right? And each edge is a data channel that transmits a finite sequence of records at runtime. So T4 would get some data from T2 and some data from T3. Once it gets the data of both T2 and T3, then it starts executing. So now we'll discuss the system architecture of the system. So the Dryad system is architected like this. It contains a centralized job manager. Similar to the manager worker paradigm in Condor, it has a centralized job manager. So this instantiates a job's data flow graph. It also schedules all the processes that are similar to the tracking manager and steering manager in Condor, schedules the processes that are supposed to run, ensures fault tolerance. So if there is a crash, it essentially restarts a job, monitors the job, and transforms the job graph at runtime according to the user's instruction. So this part is new. So the job graph can dynamically transform. We will see how according to certain directives that the user gives. So this part is new and rather interesting. So what is the execution plan or the execution overview? So the overview is like this. So the user runs a .NET application, and the .NET application creates a Dryad link expression object. So in functional programming, what we can do is that we can kind of create an expression object. So it is also possible to partially evaluate it in the sense that the function g will be evaluated on one machine, and then what will be sent to the other machine is f with the output of whatever g got and whatever g produced, and this can again be evaluated at some other machine. So partial evaluation is also tantamount to deferred evaluation, where for a sequence of actions we where each action is being represented by a function call, some of it is being evaluated immediately and some of it is being evaluated later, right? So let's say in this case we evaluate g immediately and evaluate f later. This is called deferred evaluation. So of course people who have studied functional programming would find this very easy to relate to, but for people who have not studied functional programming, I would definitely ask them to do a tutorial over here on Wikipedia or anywhere else, that talks about partial evaluation, right? So you evaluate something partially now and then defer the rest for a later point in time. So the application calls the method to Dryad table. So to Dryad table, what it does is that this method hands over the expression object to Dryad link. So in this case, so this expression is essentially an expression of a data and what needs to be done with the data. So this entire thing is the expression object. So the Dryad link system is given the expression object. Dryad link compiles the expression and makes an execution plan. So in the execution plan, what it does is first it decomposes it into sub expressions, smaller expressions. It generates the code and data for the different Dryad nodes. So of course, since we are talking of parallelization over here, the same work will be kind of divided and distributed across the nodes. So then for each of them, it may have separate code and data. For the separate code and data, whatever needs to be done over here, that is generated. And then similar to Condor, when data is being sent from a manager to a worker, we're using the same terminology. It is very well possible that this uses a big endian representation and this uses a little endian representation. So to ensure that data is transferred correctly, we actually need to make the transfer kind of independent of the exact notation. So this process is known also as serialization and deserialization, or it is also known as marshalling and unmarshalling. And once the data reaches there, all the workers need to work, and maybe let's say after that they send the data to one more worker. So this is like a synchronization point because it waits for all the other intermediate nodes to finish their work. So all of this code is automatically generated unbeknownst to the user. So all that the user actually gives Dryad link is an expression, and everything else happens automatically, which is what? Which is decomposition into smaller sub expressions, generation of code and data for the individual Dryad nodes, generation of serialization, deserialization, also known as marshalling and unmarshalling code, and the code to synchronize the data and code accesses across the nodes. So Dryad invokes a custom job manager to do all of this. So the job manager here creates a job graph. So the role of the job graph is to schedule and spawn the jobs. Each node in this graph executes the program that is assigned to it. And of course, when the program is done, it writes the data to an output table. So almost all the data in Dryad is stored in a tabular format. Recall Percolator and Google Bigtable. So the inputs also go via a table and outputs also come back via a table. So after the job manager terminates, which means all the individual tasks terminate, Dryad link collates all the outputs and creates the final Dryad table object, which essentially contains all the results. So control then returns to the user application. And so this can be a very large table. So this need not be stored in one location. It is actually a distributed table which is stored across many locations, stored across multiple locations, not across one. So what Dryad does is that it passes an iterator object. So the iterator object is essentially a handle to an object to traverse this table. And the iterator object pretty much traverses this table, and wherever the data is there in the network, it is fetched. And the iterator object is something also that can be passed to subsequent statements. So it's like a handle to the results. But the results themselves can be quite large and they can be distributed. But that doesn't matter as far as the invoking application is concerned. To get any row of the table, it just has to use the iterator object. and Dryad will automatically fetch it from wherever it is stored. Now a word or two about LINQ. So LINQ has a very deep object-oriented hierarchy. The base type in LINQ is an interface. So recall that an interface primarily defines functions of the type IEnumerable. So IEnumerable basically is an iterator where we can just go through every entry of the table. That's the base class. So it's an iterator for a set of objects with type T. So the programmer is not aware of the data type that is associated, that is with an instance of IEnumerable. It doesn't have to know. So iQueryable is a subtype of IEnumerable. So this is an unevaluated expression. So it is kind of those functional expressions that we have spoken to in the past. So basically, let us say that we want to add 2 plus 3. So so maybe 2 plus 3 plus 5. So this can be represented as f 2 and 3, where f is the add function, and this and 5. So it is possible that we can evaluate this, the first f in one machine, and then transfer to another machine for deferred evaluation. So this is of course a very simple example, but in a real life setting, such functional programs do undergo deferred evaluation, because many times the inputs that are required, like this 5 over here, this input might not be there, or the resources required to compute this f might not be there. We might need a specialized resource to compute this. So that is why the entire function is treated as an expression which undergoes different phases of evaluation at different points in time. So to implement the iQueryable expression at runtime, it of course instantiates this and creates a concrete class. So what are the prereqs to understand what I just said? Well, the ideas of object-oriented programming have to be very, very clear, particularly in the context of .NET. So it should be clear what is a class, what is an interface, and how do you instantiate a class. So these are some of the basic fundamentals that I'm assuming before I go forward. So let me give an example of the LINQ SQL syntax. So let's say I were to join two tables, score, triples, and static rank. So I were to say that the adjusted score triples is that I take each entry D in score triples and I join R in static rank as long as the document ID of score triple equals the key of the entry R in static rank. And then I select a new query score doc ID triple which contains D and R. Furthermore, what I do is I take the adjusted score triples which are essentially DR, so which are essentially tuples of D and R, as long as D.doc ID equals R.key. So this is a regular database join, right? There's nothing great with this, but this is exactly the way that we will specify it in LINQ. And so then we can create a ranked queries, which means I take each S in adjusted score triples. Then I group the SS by, the S entries by the value of the query S.query into G. And then for each such group, I take the top query results. So as you can see, this is not very different from a regular SQL syntax. So this is a LINQ SQL syntax example, which is an extension of LINQ to model SQL. So the moment that such a query is given to the Dryad system, it internally breaks it into expressions and sub-expressions. And as we just discussed, there is a complicated compiler chain that instantiates code and data, creates code data tuples that are sent to the individual machines that run parts of this query. So again, the same thing can be done with object oriented. So basically, sorry, this should be link, LINQ. Sorry about that. And so here the idea is that instead of using an SQL like syntax, we can use an object oriented programming like syntax. So in this case, this uses the same thing where we just call the join function on the static rank, and where the doc ID and R, where of course the join is on D and R, where D is the doc ID and R is the key, and both of these need to be equal, and we then create a query score doc ID triple, and we do the same thing. We group the queries based on the query field, and finally for each grouped query we select the top query results. So this query is exactly the same as the previous one. It is just that LINQ provides different ways of expressing the same thing, just to ensure that it is compatible with all the existing query languages. So any Dryad link collection IEnumerable is essentially a distributed data set. So the input is always a table similar to SQL. It's a large table, similar to Google Big Table as well. So you can partition it in several ways. So after all, a large data set needs to be partitioned among the nodes such that each node can work on a part of it. So either what we can do is we can hash these elements. So each of these elements, right? So let's assume that each of these elements we can hash them, and we can store them in the sorted order of their hashes and partition them on the basis of their hashes. This is hash partitioning. Or we can take any single column of the row, and based on the value of the column we can create ranges and partition. Or we can simply distribute the rows in a round robin fashion. The results of any single Dryad link computation are represented by the object Dryad table T, where T is the type of the data, and the subtypes will determine the actual kind of storage. So whether if it is an integer, we store it in a certain way. If it's a floating point, well, of course we then store it in another way. And we can also include additional details to specify the schema, the exact storage structure and the metadata of these Dryad tables. So what is the broad idea now? Well, the broad idea is that if this was our Dryad link system, what essentially we get in is we get LINQ expressions and we get in data. The data is stored as tables, instantiations of the IEnumerable interface. Dryad internally partitions the tables based on any one of these algorithms, hash, range, or round robin partitioning. Then the individual partition tables are sent to different machines where LINQ expressions or sub expressions run on them. And finally, we get the result, which is a table. Of course, the table is very large, so it is a distributed table where parts of it are stored on different machines. But the client that actually issued the request doesn't care, because it gets an iterator in return. And the moment it accesses something, Dryad knows where to locate the data. So all of the methods, as we have discussed in the past, even with Condor, have to be side effect free. So being side effect free means that only the part of the data that we are changing, actually that changes. So there are no global variables. Another way of side effect free means that there are no global variables, no files, nothing outside the scope. So shared objects can be distributed in any way. So the functions to access a Dryad table are serializable. Uh, so uh, so they so serializable in this case means that the serializable semantics are followed. So when I say get table, this means that I first I get the entire table. So this is like a transaction. And to Dryad table, as we saw, is a gateway function for starting any Dryad job. And we can also define our partitioning functions such that the tables can be partitioned. So we can define our custom hash partition function or a custom range partition function. So this, in a certain sense, is conceptually like MapReduce, where MapReduce partitions the computation and Dryad partitions the data. So in this case, if we look at it, a large table is being partitioned into smaller tables, right? Regardless of how it is being done, each of these smaller tables are dispatched to different nodes. And then on the different nodes, LINQ expressions actually work on the table to produce an output. They can be the same LINQ expression or different LINQ expressions. In addition, we have two specialized functions that actually run on them. One is the apply function, which applies a given function f to all the elements in the table. So we take each row of the table, or we take each cell of the table, right, within each column of each row, and we apply the apply function to all of them. For example, the apply function can be to multiply by 2. So we can take the table and multiply every single entry by 2. That would do it. Or we can have a fork function. So it's similar to apply, but the output can be not just one data set, but multiple data sets. So the fork function can take this, and the output can be like 2 tables. That's a fork. And Dryad is reasonably expressive, so it supports different parallelization and storage policies, and they can be provided as directives. So let us now discuss the execution plan graph, or the EPG. So the EPG is something like this. So the Dryad LINQ system converts the raw LINQ expressions, sorry, this also should be LINQ expressions, to the nodes of an EPG. So the EPG is a DAG. So we essentially create tasks and then subtasks, and then there are relationships between the tasks, right? The same way there are DAG functions. Furthermore, it's possible that a part of the EPG can be generated at runtime based on the values of iterative or conditional expressions. So this was, mind you, not possible in Condor. So here, let's say we can have a task. If there's an if statement, we can add an extra task. Or if the if statement, see the if statement is successful, we add an extra task, otherwise we don't. So it is possible that dynamically, based on the data, the EPG can change. So this is a rather powerful feature of Dryad LINQ. Furthermore, similar to the class add system in Condor, we specify the requirements of a job in its metadata. So this specifies what are the requirements of the physical nodes of the machines that are actually running the job, and what are the parallelization directives. What are the directives that we use to actually parallelize the tasks while generating the EPG. Second, this is new in a functional paradigm. We need to support the deferred evaluation of functions. This is something that we have to do to support the LINQ semantics. So there are several kinds of static optimizations that we can do. So these are not dynamic optimizations. These are essentially compile time optimizations that we can do. So the first is pipelining. So which means that a single process can execute multiple operations. So let's say it can take one query, so it can just kind of pipeline them in a pipeline fashion, which essentially means that, let's say, I can take some data, process it. So I can, within a node, I can have multiple threads, right, associated with a process, where one thread produces some output which a second thread consumes, that produces an output which a third thread consumes, so on and so forth. So it's possible to do pipelining within a node. We can remove redundancy, which means remove dead code, remove LINQ expressions that will not be evaluated. We can remove unnecessary partitioning. Let's say that prior to compiling, we realize that the user has specified we need to create too many partitions. But in practice, maybe the maximum number of partitions we can tolerate is 100, and the user is saying, look, you create 1000 partitions. So we can remove this, right? So the user can only give hints but not orders in the system. So we can remove this and we can only create 100 partitions based on the system we are looking at. right? So what are the two optimizations we have seen till now? Pipelining, which is again intra-node, and redundancy removal. The third is eager aggregation. So this intelligently reduces data movement by optimizing the aggregation and repartitioning steps. So which essentially means that whenever we take any data, essentially we break it down, we partition it into several pieces of smaller data. They are mapped and again they are aggregated. But let's say there are too many partitions, then the process of aggregation will take a lot of time. And also these data items can be mapped to different machines and there will be a lot of communication as well. So we can instead do smart aggregation. So maybe a single machine can process these two partitions and a single machine can process these two partitions. And maybe one of the machines can do the aggregation as well. So in this case, what will happen is that we are reducing the data movement and this will further cut down on the latency. Finally, we can reduce the amount of IO. So to reduce the amount of IO, instead of creating TCP connections for every single transfer, we can have a persistent TCP connection. And if there are different processes on the same physical node, we need not write to files, which is the default actually across nodes. So we need not use files. We can use in-memory, shared memory channels to transfer data between processes. So the main aim of the fourth point is that wherever possible, we try to make use of whatever the underlying system is providing in terms of either TCP pipes, like persistent TCP connections, or in-memory channels to increase performance as much as possible. And let's say, for example, files are slow and shared memory is fast. So if shared memory is available, we'll always opt for shared memory and not go for files. A few dynamic optimizations. Does the dynamic optimizations happen when you actually see the data and the job runs? So consider order by. So order by is one of the SQL queries. This is one of the SQL directives, which pretty much talks about sorting the rows based on a key value of a certain column. So what we do is we deterministically sample the values. So we just randomly sample the values first. We create a histogram and then we do a range partitioning. So let's say we sample the values and we find that look, the way that the values actually vary, a histogram of this would be something like this. Then maybe we create one range partition to be like this. We try to keep the area under the curve the same. So we can create, some sort of intelligent sorry, this will not be there. Intelligent range partitioning based on our sample. So this will ensure that each physical node is given the same number of entries to sort. Once we have partitioned the ranges, then we can kind of divide the input based on the ranges among the nodes. Each node fetches the inputs assigned to it and sorts it. So clearly we can also pipeline these two actions of fetching the inputs and sorting them. So this can be done. And so this is one example where we need to see the values at runtime and then first, so this is exactly how TerraSort was implemented. First do sampling to give an idea of what are the range of values. From the histogram, we figure out a range partition. We perform a range partition on the table of data. We assign a range to each node. So the node basically fetches data and simultaneously sorts whatever it has fetched. So this can be pipeline. So this is an example of a dynamic optimization that is performed in the Dryad LINQ system. So this is kind of a pictorial representation of what was just described, where we have deterministic sampling first, and deterministic sampling provides us the histogram and the ranges. Based on that, we allocate a range to each node, and it pipelines the fetch and sort. So the EPG over here is a virtual execution plan, and Dryad LINQ has to dynamically generate code for each EPG node. So this we have discussed in the past as well. So what Dryad LINQ does is it generates a .NET assembly snippet. So .NET has its own assembly language syntax that corresponds to each LINQ sub-expression. It contains all the code for serializing data and I/O and for ferrying data. So all that is built in. The user need not bother about any of these steps. The code of the EPG node is generated at the computer of the client, which is the job submitter. So the nice thing about .NET is that it is actually a virtual instruction set similar to Java bytecode. So we can always generate the .NET code on any machine, and when it physically runs on the actual machine, there is a translation between the virtual code that .NET has generated and the real machine instructions. So this is very similar to the way that Java and Java bytecode work. So the EPG code, node code, is generated at the computer of the client, the job submitter, because it may depend on certain things of the local context. So similar to a Condor shadow, there might be local files that are in the local file system. There might be environment variables. So all the values in the local context get embedded in the function expression. So which means that if, let's say, this is the entire LINQ expression, whatever can be brought from the local context, all of that is kind of embedded in the expression. So then we have a partially evaluated, so let's call it a P, a partially evaluated expression. This partially evaluated expression is now dispatched to each of the individual nodes for further evaluation, for deferred evaluation. So we use .NET reflection. So .NET reflection is basically, so reflection is a general concept and it had come in Java a long time back. So in this context, actually the .NET virtual machine takes a look at each class or takes a look at all the libraries and finds all the libraries that it is dependent upon. So those dependencies will have dependencies. So the transitive closure is pretty much the set of all the libraries that, let's say there's library A, all of the libraries that it is dependent upon, all of the libraries that they are dependent upon, so on and so forth, till we have captured the entire set. So the EPG code and all the associated libraries are shipped to the cluster computer for remote execution. So this is a marked departure from what Condor does in this situation. So Condor actually sets up a channel between the sandbox and the shadow, such that if the sandbox needs something which the remote machine does not have, so then the sandbox in Condor would actually send a message to the shadow saying that, look, I need this. The primary reason being that these are actually separate setups, and the notion of deferred evaluation was not there. So, and also the network speed those days was slow. And also the other thing is that maybe they use different versions of an OS. Any code over here would actually not run over there and vice versa. But because of the fact that .NET, like Java, is a virtual ISA, so it is very portable across all kinds of machines. The network is fast. Hence, in this case, we don't do what Condor does, but instead, we ship the EPG code and all the associated libraries to the remote machine, right? Everything is sent. A few miscellaneous items. So, there are extensions of the LINQ system. So, we have plink, where it runs a sub expression in a cluster node in parallel using multi-core processors. So that extension is there, where the users can supply annotations, and these are similar annotations similar to parallel programming variants like OpenMP, where it specifies how these iterators are supposed to run. And also LINQ interacts with SQL. We have already seen an example how, where it can directly access SQL databases, save internal data sets in SQL tables, and also translate LINQ sub expressions to run directly as SQL commands. So a certain interoperability with SQL was added. So if you would actually see the design which is based on tables, at least at this level, it is similar to SQL, even though differences arise later in terms of deferred evaluation and usage of the basic .NET system. But at least there is a certain level of high level compliance which allows a degree of interoperability even with traditional database systems. How do we debug a massively parallel application? Well, how did we deal with this problem in Condor? In Condor, what we did is we had the notion of a rescue DAG. So here what happens is that if the post-processing script of a job said that a given job could not execute correctly, then we take the entire DAG, we cut out the part that executed correctly, and then again cut out the part which didn't execute correctly. This can then be analyzed by the user, and the user can figure out, out of this which job didn't execute correctly. That part again can be like repatched, and then the entire DAG can run once again. So .NET, of course, had the advantage of the Visual Studio interface to debug many of these things. And the great and the really praiseworthy thing that Dryad LINQ added is a deterministic replay model, which means that given the fact that these are actually kind of functional programs which are side effect free and which do not rely on anything which is outside the environment. So essentially, if you look at any LINQ sub expression, it's like a program where all of the inputs are specified. So every time that you run this program, regardless of wherever you run it, because .NET, like Java, is provides a degree of platform independence, if the inputs remain the same, the output has to remain the same. This means that we can, let's say that a given job, a given task failed on a remote node, we can then bring it back to the client machine. We can provide it the same inputs which it got on the remote node, and we can essentially debug it line by line and see exactly what happened. So we can pretty much replay the entire execution event by event, right? And view the outputs on the local machine, figure out what went wrong, fix it, and send it back. So this is the advantage that there is no non-determinism in the execution, which is actually there in other frameworks like MPI and so on. And non-determinism would only crop up if this would depend on something which is not really an input but produced by some other task at an intermediate halfway state. And then depending on the latency of the network, the execution can be non-deterministic. It can either get a certain event or not get a certain event. The time of getting it also matters. So all of this has been avoided. So this is simply a LINQ sub expression. It is given a set of inputs, right, fully or partially evaluated, and then for the same set of inputs, the output will be the same, the behavior will be the same on all machines that support .NET. And so this has taken care of the performance, sorry, of the debugging aspect very well. So along with correctness debugging, we can also have performance debugging where we collect detailed execution profile information. For example, it is possible that a given job runs very slowly. So to actually fix that, we can collect detailed runtime statistics to figure out why a job ran slowly. And then from the information, maybe we can find out why. So the execution setup, it was a 240 computer cluster. Each node contains two AMD Opteron nodes, which are server processors. 16 gigabytes of main memory, which was okay, which was considered good 10 years ago. The first was TeraSort, where we sort a terabyte-sized data set. And so essentially the idea here was that, so of course it's a terabyte when we consider 240 nodes. Otherwise, if we consider n nodes, it is 3.87 gigabytes per node. So the way that they did the experiment is that they considered a terabyte of data for 240 nodes, but they also considered 100 nodes, 50 nodes, and so on. See, the number of nodes is n, the data was scaled accordingly, so it was 3.87 n. So the first, so as we discussed, TerraSort. So TerraSort, the execution time, so again the data was kept constant per node. So when you had a single machine, the execution time was 120 seconds. And it quickly jumped to 250 seconds, and kind of the execution time was like an asymptotic behavior, with it kind of saturating at 320 seconds. And of course, at one point with 240 nodes, the data was 1 terabyte. So the reason for this, asymptotic behavior, so of course the starting point is not 0, it is 120, is that as we add more nodes, there are more overheads in terms of EPG compilation, dispatching the inputs and the code to different nodes, network delays, switch delays, and so on. But still, it's not that bad, given that from 1 to 240 machines, the execution time just increased by around 2.6, 2.7 times, right? It didn't triple. And sorting a terabyte size data within 5 minutes with rather simple code with the partitioning mechanisms that we have discussed is genuinely praiseworthy. The other was a Sky Server benchmark, which contains a lot of astronomical data. So it was a three-way join for two tables. One was 11.8 gigabytes, the other size was 41.8 gigabytes, and the number of machines was varied from 1 to 40. So the speed up increased. So they compared this with a baseline Dryad system that does not use the LINQ expression, does not use this mechanism, but just uses the basic distributed framework. So of course the speed up was much higher with Dryad when it increased from 1 to 24, sublinearly of course. And this went down from 24 to 19 in the case of Dryad LINQ. But well, if you think about it, it's not that bad, given all the automatic things that Dryad LINQ actually does, and how much it makes programming easier for us. So the paper that describes the Dryad LINQ was published in OSDI 2008, around 12 years ago. So for those days, these were fantastic results. So now, of course, because of an improvement in hardware, the results have become better, no doubt. But the important point is that for leveraging a cluster of heterogeneous machines, we need systems like Condor, of course, which was like, which saw its heydays from 1990 to let's say 2005. And then, of course, the Dryad LINQ kind of system. And now, of course, we have many more systems. So Condor did spawn a large number of other projects like LSF and Load Leveler and so on, which are still heavily used in companies. And Dryad LINQ has also also spawned a large number of similar projects where we are talking of really expressive mechanisms of describing a parallel execution. And the underlying framework actually does a lot for us, and that too automatically. So this is a continuing area of research, because along with regular processors, we have GPUs and accelerators and so on. And so then for GPUs, of course, we have OpenCL, which is not exactly distributed, but this is kind of in that direction. So we have many such frameworks, and we'll continue to have. So this area is clearly not going to die over here. As the diversity of computing devices increases, we'll have more and more of such frameworks which actually do more of the planning and scheduling automatically.